This carries on from what we were looking at on Friday, and it's a technique using the t results for solving trig integrals. A reminder of your t results, t equals the tan x on 2. Now, I'm going to introduce a new t result. We know sine x is 2t on 1 plus t squared, and cos x is 1 minus t squared on 1 plus t squared. So our integrals that we're going to use this for involve sine and cos, so they'll become important. But there is now another t result we need, and that is for dx, when we're doing our substitution. Here we go. Well, the t dx, differentiate tan, you get sec squared. So we've got a half sec squared x on 2. Sec squared I can change to 1 plus tan squared, and that becomes 1 plus t squared. Well, that's the t dx, so therefore dx to t is the reciprocal, meaning dx equals 2 to t on 1 plus t squared. No, I do not expect you to derive that each time, although it would be handy if you do know how to, just in case you get asked to. But to me, that's just another t result. So just like you can quote sine x is 2t on 1 plus t squared, you can quote dx is 2 to t on 1 plus t squared. Okay, so let's use it. We want to integrate something like this. dx on 7 plus 6 cos x. So I still write down what my substitution is. I'm going to write down that t equals tan x on 2. And just to remind myself, yep, that now means I know dx is 2 to t on 1 plus t squared. I don't bother writing down the other t results. But then we go and substitute in. Now the nice thing about it is because we're using it for when we have sine and cos, and also look at dx, all three things have the same denominator. They're all over 1 plus t squared. So you can always cancel the denominators out by multiplying through by 1 plus t squared. In fact, sometimes I won't even put that second line in. I'll just jump straight to the bottom one. And so I'll just write the top. But I have to be careful, of course, and remember that the number 7 there, I have to multiply by 1 plus t squared if I do it that way. So we end up with 2 to t on 7 plus 7t squared plus 6 minus 6t squared, which tidies up to be 2 to t on 13 plus t squared, which is our inverse tan. So we get 2 on root 3 inverse tan of t on root 13, but of course we need to get the x's back in there. So we have this wonderful expression. 2 on root 3 inverse tan x on 2 on root 3, plus of course a constant. Now with these you're going to end up with a lot of quadratic denominators because the t results will involve multiplying through by 1 plus t squared. I mean, I ended up with a basic inverse tan, but it could, of course, end up being any of those different quadratic denominators that we looked at. Just a note though, that was for the substitution t equals tan x on 2. If it was t equals tan x, just to show you, we'll go through the same process. The t dx is sec squared, 1 plus tan squared, becomes 1 plus t squared, so we end up with dx being the t on 1 plus t squared. Basically, it's this. If t is tan x on a, if that's what you're letting t equal to be, and what will end up happening, and I'll derive it just to prove it to you, is look what we end up with. We always end up with a to t on 1 plus t squared. So our standard one where it's x on 2, we end up with 2 to t on 1 plus t squared. But basically, they always match. Told you it was going to be a quick one.